NAU has not crashed and burned yet. We still are teaching electrical engineering courses in the fall, and everything's wonderful. This is, I am recording. Okay. It's pseudo spring break. We're going to start Flash. This will be where we catch up, basically, because we need to get to MRAM by April 1st. So we need about 4 days for Flash, typically. We don't go into as much detail as we did with DRAM. A lot of the architecture is similar. This first day is mostly talking about the basics of how the Flash cell works and some historical trends on memory, kind of the business end of this. So that's where we're at right now. We'll get into more of the gory quantum mechanical details later on.
Flash was the non-volatile.
Yeah, it's what's in your solid state drive. Okay. It's non-volatile and it's slow. It's slow because we have to do really bad, horrible things to the cell to write to it. Very aggressive things. This is a job ad. You may be interested in, this was an old one, but you may be interested in this job. You may not be interested in this job. What I recommend you do about this time is just start looking at job ads, thinking about the skills you'll have, you will need to have for the job you ultimately want. If you always working towards getting the skills for the job that you want, it may not be the job you have now, but if you work towards that, you'll get there eventually. You'll find that opportunity for what you're looking for. A lot of this stuff you should be able to handle, but FPGA design, you know, get a couple of years under your belt somewhere as a test engineer. ASIC design, that's a little bit harder to do, but if you understand the analog side and the FPGAs, you can usually get there. Simulation and verification, be able to, you know, use Mentor Graphics, Cadence, or some other high-level tool, Verilog and VHDL. And this is from Seeker, and I know the guy who's the it's a family-run company. I know a couple of the Andersons. They used to go to NAU, and they'd come back and give us piles of old equipment that are sitting in my IEEE room.
Yeah.
Okay.
Which I guess countries are going to be reorganizing this week / next week.
Good. Okay. So we're going to do a brief history of Flash, and this is a good thing because I've never talked like this before, kind of on a business end more so, of how ideas get started and what usually happens to them. We'll talk about some different kinds of non-volatile memory, and we'll look at some business trends. Some of this stuff is old, but the trends are continuing. And I don't know if I'm teaching memories next spring or not. I don't know. This is the last time I ever teach this class, so I have very little motivation to update things. I updated things a little bit last semester, last year. I usually update them verbally. Okay, so what we really want is the universal memory, one memory to rule them all. It has the best of everything. It's low cost, it's super fast. I can put a whole bunch of memory cells in a small area. It doesn't lose its memory when I turn the power off, and I don't have to refresh it. And the memory stays, it's durable, it stays there for a long time. So far, we don't have the universal memory. We split our computer, and there's a slide for this, but we split our computer architecture up and split the different types of memory up based on the strengths and the weaknesses of each one. These right here, the first four, they fit in the category of emerging memories. The two that I will spend one day on a piece because I work with them in the lab, so I know a little bit more about them, are MRAM and ReRAM. FRAM is ferroelectric RAM, and that is kind of at the stage where people have a design for it, but they haven't really commercialized it yet. Ferroelectric RAM, it's been like that for at least 6-7 years. There's some issues with it. This phase change memory is actually being sold under the name Optane from Intel. It was originally developed by Intel and Micron, and then they kind of split ways. They parted paths on this. Micron has their own version and Intel has their own version now. We'll talk a little bit about that today, but that's probably about it. And these right here are some older technologies that are still in use. The OM at the end of it is, or excuse me, the ROM at the end of it stands for read-only memory. So you put this in places where you don't want the end user to change it. Things like the serial number of your machine, the BIOS, the
But you can update
you can, I know, believe me, I know.
You can, but it's unadvised.
Okay.
I had to do that like IT.
There was this guy that this test engineer I worked with at JPL, and the lab was just this big mess. And he would just go in there and randomly change the BIOSes on the machines. I mean, it was just all the time. And none of the machines had, none of our computers had sides on them, because he would just take the motherboard out of one machine and put it in another one. And then, I mean, he was just swapping cards. You didn't know what was going on. You could not walk into that lab and do anything without getting Chris Wrigley and saying, hey, what computer do I have here today? And can I do this job with it?
So did you say that was it Jack with that DRAM puff by like there was like the thing on the FPGA that I think was the FPGA that you had, you said that he wrote to the read only.
No. There was that wasn't Jack. That was when Ian was working on it.
Yeah, he wrote like all zeros to it and then
To-
cut power.
No,
You can do that. You can force a write to the read-only memory. I thought
no,
hardware wouldn't even
you
let you.
cannot force a write to read-only memory. There is okay, one of the control registers inside of the DRAM controls the speed of refresh. And the idea that they put it in there is maybe you've got a sensitive application, or you know you're going to be running this chip a little bit hotter than normal. You can speed up the refresh. We tried to use that refresher. We tried to use that refresh register to write a 0 to it to say don't refresh at all. And the tool we were using just basically came back and said, I'm sorry, we can't do that. You read it back and it's not 0. It was not an allowed state for that register. So we tried setting it as long as we possibly could. We couldn't set it long enough. Yeah. And then me and Jack tried to win a totally different route.
So move the universal memory, hopefully we don't have to throw it in the
Yeah. Flash is different. It's what we replaced what we called the hard drive, the magnetic hard drive in your computer. It is the solid state drive. It's got the beauty of being non-volatile. It's got a problem in that it is extremely slow, and we'll talk about why it's extremely slow. Sorry, I've gotten into the side conversation. I don't know what you guys heard or didn't hear of that. This is ferroelectric RAM. It's somewhat making a comeback. Basically, it's similar to DRAM, but it uses a ferroelectric layer instead of a dielectric layer. So in that capacitor, it's got a ferroelectric in there. You put an electric field across it, and it shifts the ions within that dielectric ferroelectric layer from being spin up to spin down, and it changes the effective resistance or the voltage that you're going to read across the device. Non-volatile, still fairly experimental, and it's been fairly experimental for a long enough time. I don't think it's going to like break through anytime soon. Yeah. Okay. This is MRAM. We've got a whole day on this later, and then, well, actually, we got a week and we got a day and a half because Dr. Cambo will talk about it partially. The people who originally developed MRAM were Motorola, and yeah, this is probably more on the business end. Motorola got split up, and piece of it became Freescale, and then Freescale got sold to NXP, and then they sold off the memory division in that split, and that became its own separate company called Everspin. So this company has its roots in Motorola, and I've been down there. It's very Motorola.
Very Motorola.
It is.
I like Motorola as an adjective.
Motorola is an adjective. It's magneto-resistive random access memory, and we'll do a whole. I will do a whole day on this, and I can tell you now that this is not the pen layer. I copied this from Wikipedia, and I realized this today. This is the pen layer. Wait. I don't know. We'll talk about how it works. What you're going to do here is you're going to force a current through this line, and I'm not writing anymore. Oh, because I've got the eraser on. Good. I'm going to force a current through this line, and the current, current going through a wire generates a magnetic field by the right-hand rule. If I force the current this way, I'm going to force a magnetic field going in that direction. If I force, or going this way, if I force the current this way through the wire, the magnetic field goes in the opposite direction. And I can use that magnetic field to program this free layer. And whether or not the magnetization of the free layer matches the magnetization of a penned layer that has a permanent magnet will tell you whether you've got a high resistance between there or a low resistance. It's a little bit more complicated, but I'll have a whole day to go through that. It's non-volatile, it's small, and it's fast. The problem with this one is density. Right now, the parts we got from Everspin last year are 16 megabits. It would make the universal RAM, you could make the universal memory out of this, except for cost and density. It's fairly expensive because I have to build a CMOS process, take it to another factory, and put a magnetic process on top of it. So it's like I'm paying for the ice to have the processing done twice. Density, cost. It's got some niche applications, and we'll talk about those when we talk about MRAM.
What's the difference between small and density, I guess?
Small and it's how many of these you can put on one chip reliably.
Okay.
So you could make let's say you could make a really small 1 nanometer cell, but you could only put 4 megabits on a chip because of all the readout and everything, and maybe it would overheat, or maybe the reliability wasn't good enough to get it above a 4 megabit size.
So small would be the actual physical
Size of the cell.
And then density would be like how crowded it is.
Or how many megabits you can put on a reasonably sized chip with a reasonable yield would be the density. Okay, good. We're talking about something other than DRAM. We spent like a whole half of the semester on DRAM. Okay, this is ReRAM. It's being made by, oh yeah, there's also a company called Crocus that makes MRAM. You will never hear Dr. Kimbo talk about them.
Does he not like them?
No. Okay, he's not a big fan of Crocus. So ReRAM, our partner in the lab is Crossbar. We've also worked with ASU, Virginia Tech, University in New York, I can't remember who they are, Bridge in Florida, and a lot of other people. But so far, Crossbar has given us what we really want. This is resistive random access memory. This I really believe in. It's non-volatile. You can build, it's not a 1T, 1C. You can do this with one diode, one ReRAM cell, 1D, 1R. Okay.
The 1D, 1R.
1D, 1R. So it's smaller. Crossbar is actually able to build these inside the via cells between layers. So they're tiny. You can integrate this directly into a processor. And the way it looks in its pristine state is it looks like what's called an MIM capacitor, metal, insulator, metal. And this is before we form it. In the initial forming, you make these tiny little filaments across here by putting a high electric field across the device. Generally, takes about 0.6 volts to start programming it. But it's a very narrow layer, so there's lots of volts per nanometer. When I program it, I make these filaments, and in the on state, the filaments stay. The filaments are formed by ion migration. It's literally atoms moving from place to place inside the cell to make conductive filaments.
Is this not a solid?
It's no, okay, it's like tantalum. It's like a ceramic. It's like glass. It's solid. When you put a high enough, well, this is really what happens, because I studied this last summer. When you put a high enough electric field across it, locally inside this little filament, you get temperatures of up to 5,000 Kelvin. It's hot enough to melt tantalum. It's hot enough to melt ceramic locally. You can touch the wafer. It's very local heating. It gets melty, the tantalum gets melty, and the ions move around.
That's why you need tungsten.
Yeah, you tungsten. That's why you need. Well, no, it's local heating.
Okay.
It's hot here. It's cold over here.
So it has really poor heat transfer capabilities to that, so you don't then you don't burn yourself when you touch it.
Yeah. And it's all internal to the cell. If I want to, and so I build this conductive filament in there. If you have a filament, it's low resistive state. To erase it, I put current through the other direction, and the filament breaks, and it's a high resistance state, and it stays there forever. Working on getting the density up so it's more competitive with flash. It's still more expensive. This is what this is what's on the Optane drive. And the way I discovered how this works is I was up at Micron, and I'm looking at this thing underneath an electron microscope, and I'm just like dumbfounded. And the technician or the engineer, whoever he was, the guy running the thing, is standing next to me, and he goes, "Do you know what that is?" And I go, "Yes, I know what that is. It's a crystal, but what is it doing there?" There's nothing crystalline inside an integrated circuit normally. The way this works is they apply energy to this, and when they apply energy to this crystal, it becomes non-crystalline, it becomes more amorphous, and I'm not too sure exactly how all this works, but we have two states here. We have a crystalline state, a non-crystalline state, and between the two of them, they are, they have different electrical characteristics, so they can store memory that way. The problem with this is, in order to go from a crystalline state to a non-crystalline state, those ions have to move in a semi-random pattern. And what happens is the ions move, and you'll start to see ions out here, and maybe a couple of ions like this shorting to the word line. So they've got some reliability issues. But it's really good, and it's fairly expensive, and it's faster than flash. It's the Intel Optane drive. That's their brand name.
Oh.
Yeah. ROM is read-only memory. It's for stuff that I don't want people to change ever. Maybe it's the control unit for my DSP. And I don't want to do software upgrades on this because I've got this memory that's tied to the hardware as it is. We usually do this for very high volume applications because it's expensive. It's like building a custom IC for a memory. And you can't change it until you change the mask. You just have to build a new IC. You basically just break fuses, break connections, or leave connections open, and that will determine whether you have a 0 or a 1. Programmable read-only memory. This is sometimes referred to as an OTP, a one-time programmable device. There are FPGAs that are one-time programmable too. They're cheaper than the ones you can reprogram. And those you put into production because they're cheaper if you don't want to change the programming. You blow a fuse. You either blow the fuse like we have done here. I probably should use my little thingy, not my pointer. Or you can leave a fuse intact and control whether it's a 1 or a 0. You've permanently burnt that fuse out, so you cannot go back. The ROM, what I'm trying to say here, is the ROM is, when you do the mask, it is the cheapest unit cost you can have. But you have to have at least, like 100,000 of these units before you can break even on this. With the PROM, it's going to be more expensive per device, but you can get, if you only want to use hundreds of them, you don't have the startup costs that the read-only memory has. A different trade-off. Oh, I hated these things.
Reading about them.
I've used them. Basically, you had to tape this little cover over the top of them. Otherwise, ambient light would erase them at random. This is an electrically erasable or erasable programmable read-only memory. The way you erase it is you put it in its own little tanning bed, and that's what we called it. It was this little chamber with a UV light, and you leave it in there for about 10 hours, and then you can reprogram it.
Okay. So it will erase what's currently on it.
Right. The problem is that they weren't that stable. You could use them for maybe like, a few weeks, and then you'd have to reprogram them anyways, erase them and reprogram them. But they were good for testing things. Kind of like an early pseudo FPGA. I could load a program into here, throw it in my bank of test equipment, then program the test equipment using that, realize I have a bug, take it out, put it in the tanning bed, go back to my test equipment with a new one, and find a new bug, and then repeat this. So I had about 10 of these going at one time to help me debug my programming. Yes, I just said I programmed. Flash was invented at Toshiba in the mid-1980s. Yes, what?
That's kind of funny.
Yeah, and then like, what is it? It said the rating too was like it didn't really like pick up very, very quickly either. Like that Toshiba's rendition of it didn't.
Nobody knew what to do with this. There was a big breakthrough that it was a floating gate transistor, but you read and write to the memory in chunks. There's two main types of architecture. There's the NAND flash, which is pretty much dominating now. With NAND flash, you read out a block at a time. With NOR flash, you get true random access, and it makes more sense when you look at the circuit diagram. So it's more of a direct replacement for EEPROM. But it's kind of lost momentum. In the early days, NOR was winning first, and now it's mainly NAND because we want to read out big chunks of memory. And when you can read out big chunks of memory faster with NAND flash than you can with NOR flash. NOR flash, you can read out individual sites faster. Okay, where are we going to the history here? Toshiba basically failed. Lots of people failed because they couldn't find a good application for it. The first ones who came up with an application that was usable was Intel. and it was a direct replacement for another chip that people were already using. They used the same pinout, they used the same input voltage range, and they had put charge pumps on the chip to make it work, and all this stuff. But it was all people had to do was just slap this down on their circuit board instead of the other part. It was cheaper, and that's what got people buying it. You know, just imitating the old stuff. Right. The big problem with flash, internally, you need really high voltages to program an erase, 10 to 20 volts. You need a huge electric field. This is based on tunneling. It's a quantum mechanical effect. If you're a human being and you try to walk through a wall, there is a finite non-zero chance that you will walk through the wall and come out on the other side in one piece.
Yes.
It is a very small chance. You would probably have to sit there and bang your head against the wall for all eternity, and then eventually you get across. Okay.
The movie, The Magic Stair Goes.
Yeah. Oh, I actually saw that.
Yeah,
Okay.
it runs through the wall.
Ben and I watch the same movies. That's scary. Quantum mechanics, the version of this is I'm an electron, and I come across an energy barrier that is higher than the energy I have as an electron. If the barrier is thin enough, I can possibly tunnel through and come out on the other side without passing through that barrier. And the probability of that happening is much higher. Okay, this is what flash uses. Is basically, I've got this gate that's isolated, it's floating, and I'm going to go across this energy barrier as an electron, and I'm going to get inside this floating gate with no electrical contact. Takes a lot of energy to increase the probability of that happening. We'll go into the details later. Another,
Do our phones not use flash?
what?
Do our phones not use flash?
Your phones use flash.
Oh, they just like charge pump or something up to a high enough voltage?
Yes, they charge pump it internally.
Good old charge pumps.
Yes, because they cannot, nobody wants to have 10 volts coming off your battery. So instead of taking, you know, your battery might be 5 volt, 4.5 volts or whatever it is. What they do is they take that voltage in and they draw more current to get up to 10 volts. So it's kind of like the power is the same. It's conservation of power or something like that, where the current gets higher and the current gets lower and the voltage gets higher, or something like that. Okay. And so they started doing more packaging when they went into the more different types of packaging, the memory cards, those little memory cards you put into your phone, or you can put into your computer or your camera. Yeah. What are they called?
SD cards.
SD cards. Thank you for the vocabulary. SD cards, those are all flash. And that really helped the flash coming out. Yeah, digital cameras, MP3 players, and cell phones. Yeah, what?
Look at that, there it is.
There it was, and I wasn't even looking at the slide. I wasn't reading it. Okay, so in 2013, memory is a very cyclical industry. When the economy's doing good, the memories business is doing good. When people are buying a whole bunch of new computers because suddenly they have to do everything on Zoom and their whole life gets rearranged, the memories business does really good. In the tech bubble, the memories business did not do so well. You guys probably don't even remember that.
Great year for Micron.
It was a very good year for Micron. NAND growth is slowing, but it's just changing forms. If you think about your phone, you know, I can remember back, you know, my second phone ago, I wanted 64 gigabytes on it because I stored all my music on my phone.
Same.
And now I just download it. I'm continually streaming. And I still do have over 128 gigabytes of music. But I'm yeah, kind of slowly losing it. Slowly losing my connection to the music that's on the memory cards. That's what I was trying to
It's a
say.
lot of songs.
It is. It's
like,
yeah. They're
the old iPods that had absolutely crazy amount of space on them for the time.
right.
Like, and now that I think back at it, I do something like 500 megabytes.
Yeah, I gave up because I can't get more than 64 meg on my phone. But what's happening now is nobody is storing all that music and all that stuff. They're streaming it. But you know what? All that stuff you stream has to be stored somewhere. And it's stored in the cloud. Where is the cloud? It's a big server farm somewhere in San Jose or upstate Oregon, or there's one in Iceland because it's cooler and the heat dissipation is less. They literally,
You're reaching at songs in the air.
yeah, they're storing it somewhere. So where the memory is getting sold is changing. But the memory that's in those server farms is very high-end memory. The stuff that's in your phone is not so high-end. So it's a better quality of memory. So again, it's being sold for more dollars.
Dream of it that there's a server farm that in France burned down recently.
Oh, Microsoft had the brilliant idea because, okay, cooling is a big deal on server farms because they have to keep the temperature down on all these SSD drives in order to optimize their performance. So they got to keep them at a nice, 72 degrees, but they're generating heat all the time. So their air conditioning bill is huge. And actually, to save money, they do move server farms to Iceland. Microsoft had this wonderful idea. What they were going to do is they were going to put it underneath the ocean. And see, this way they would have water cooling going back and forth. But the cost of actually like sealing the whole server farm out from the salt water and the pressure and all this stuff and repairs and things like that, it just, it didn't go anywhere. But they did build one.
Underwater city.
Underwater city.
Let's put everything like underneath the Hoover Dam where there's the big.
Yes.
Yes. Well, actually, isn't no, never mind.
Okay.
I definitely get, but it isn't. No, yeah, no.
Okay. All right. So the NAND flash, pretty much, here's Micron. Here's the one we care about. Is the red part right here. They're holding pretty steady at about 12% of the market all the way across. Samsung is always the major player, and Toshiba has kind of been losing market share. Micron just kind of like always holds steady. SK Hynix.
I've never heard of SK Hynix.
They are a Korean company.
Oh, okay.
Not quite as big as Samsung, but they are pretty good. Intel, again, just hanging in there. It's not really their specialty. Here's when SanDisk went into the market for flash. They took over quite a bit of market share. And what?
It was until 2013. I feel like it should be older than that. I thought SanDisk was older.
I think they were around longer, but they just weren't in the flash market. It could have been. I don't know. Or this chart's wrong. Comparing revenues and market shares. Again, Micron's right about 12% across there. There's one kind of interesting. Market trends. Okay, so this is what's going on in out to 2025. Oh God, this is current. It's an old slide. 2015, you see this 3D flash is kind of a niche and it's new and coming in. And 2D flash is the blue. And you can see 2D flash's market shares going down and 3D flash is going up. But overall, we're selling more flash. There's a good picture of 3D flash right here. This is 3D NAND flash. basically what I've done is I build one wafer of flash memory, and I stack it on top of another wafer of flash memory, and I stack that on top of another wafer of flash memory, and I keep on going through this. When I address a particular location, I'm going to address that location in every single one of the stack layers. So there's these vias going through that are going to do addressing through there, and I'm going to get the data out in parallel all at once. So I can get a lot faster throughput, and I can get rid of some of the problems. Kind of a yield issue. When I was at Micron, I guess it's been about 2 years now, they saw this little flash drive that was about this big, and it was 1 terabyte, and they had it was a prototype. They had 100 layers of flash within there, stacked on top of each other. The yield was kind of low, and they were still kind of in that stage, but it's still kind of experimental, yeah. But you can see that you can stack a lot more memory in a lot smaller area and get it out faster using 3D NAND flash. Okay. Applications, we've already kind of talked about this a little bit. Portable media players is this light blue. It's going away. This is your iPods. They're not selling a lot of memory for iPods anymore. The handsets kind of peaked in 2012, and then people started storing things on the cloud, and it went down. Tablets kind of went up for a while, and it's starting to go down too. We're not storing more stuff in the cloud. This SSD, the orange thing, is what's growing so much. And what that is cloud storage. When Brad Turcotte, when he graduated from NAU, I want to say like in 2015 with DJ, 2015 or so, his first job was at Intel at a server farm. And basically going through there and just changing out memory cards and things like that. Now he's, last I heard, he was a manager somewhere, and it wasn't that long ago. And he's went to Silicon Valley, so when you're there, you can just hop from job to job as soon as you get a better offer. You know, you go across the street and get $10,000 more a year. You go back across the street, you get another $10,000 more a year, and nobody stays in any place longer than 2 or 3 years.
That's pretty cool.
Yeah, but there's lots of jobs.
Wow.
You just it's getting your foot in the door and managing to cough up rent for your first apartment there, which may be a minivan.
There, yeah, but aren't a bunch of people moving out of Silicon Valley?
Yeah, because of the cost of living.
Yeah, they're like moving to like Nevada and Phoenix.
And Austin.
Yeah, and Austin.
And yeah. Okay, so things that we're going to be talking about here as we compare these memories. Retention is the length of time that a memory can keep data. Even flash, they're typically spec'd at about 10 years. And there are whole pages of flash that are going bad at any given time. Reading and recall. So this is the process of reading the data out, sensing the charge level or the threshold voltage level if it's flash, and getting that into your system. Writing to memory, we've talked about that enough. You should know what that is. You set the charge level on the DRAM, or you set the voltage threshold level on the flash cell. In DRAM, we have destructive readouts because every time we read the data out of DRAM, we destroy the data. We have to write it back immediately. In flash, you don't have to do that. Unpowered retention. That means when the power goes off, does it save its memory? Flash does, DRAM doesn't. And non-volatility is the property retaining data without a power source. I can tell you from personal experience, DRAM's a lot more non-volatile than people think. There are cells that it can take hours before it loses its memory. But, you know, 1% of them lose it in in a few seconds or less. So that's why we keep writing back to it. Yeah.
Is there a reason that motherboards use like a little CMOS battery to maintain power instead of just writing it to non-volatile stuff?
We'll talk about that when we get to MRAM. That's one of the kind of the niche markets for it. But there's a couple of ways you can keep the memory in DRAM. You can keep the memory in DRAM if the power goes down for a short amount of time, if you have a battery backup or some kind of super cap there. That's expensive to do. Inside of solid state drives, the flash cells are slow enough to read and write from that what they do is they read a whole bunch of data when they're trying to have big bursts of data. They read a bunch of data from different chips at the same time, and they store it all in a DRAM. Now that DRAM's got to have battery backup on it. And the battery backup is big, bulky, and expensive. But if you have a high reliability operation, like say you're making trades on Wall Street, and you want to do them really fast, and it's going through this SSD. If you lose data for a second, you may have lost a couple of hundred trades and no way of getting them back up at that point. So that is one application of MRAM is right there, is it replaces that DRAM as the fast throughput part of the SSD without battery backup. Okay. Yeah, we'll talk. You'll read an app note on that in about a week. Okay. So this is the basic flash cell. It's this funny looking transistor with two lines on there. It's a floating gate. You literally have your gate voltage here is tied to the control gate. And the rest of it looks like a normal transistor. So this isn't 1T, 1C, this is 1T. No C. The C is kind of buried in there. There's the C. What I do is if I can put a really high voltage between the gate and the body here, I can give the electrons enough energy that they have a reasonable probability of jumping into this floating gate and getting stuck there. If I get enough electrons in the floating gate, I'm going to change the threshold voltage of the device. So let's say this is the erase state, erase. And this is V threshold right here. When I program it, I put enough electrons in the gate that I shift the threshold voltage, V threshold 2. Now when I go to read the cell, what I'm going to do is I'm going to give it a voltage, I'm going to put like this voltage on the gate. It's enough to turn on the transistor if it's in the erase state, but it's not enough to turn on the transistor if it's in the program state. So this is what determines whether it's you read out a 0 or a 1, is that shift in the threshold voltage. Again, takes a lot of energy though to force these electrons into this floating gate. But they stay there because it takes a lot of energy to get them out again.
Do you just kind of do the same thing in reverse for within the load?
Yeah, there's two basic mechanisms for doing that. One is called Fowler-Nordheim tunneling, and the other one is channel hot electron injection. The Fowler-Nordheim tunneling I've kind of already talked about. You just tunnel through that barrier. The channel hot electron injection is I basically put current between the drain and the source that has a lot of electrons with a really high energy, and those very energetic electrons tunnel through that way. Okay, so that's basically the two ways to program it and two ways to erase it. And there's a table for how we do that later. I forget which one we use where. So the threshold voltage shift, I already talked about this. Wow, I got ahead of myself. I basically put some charge into that floating gate that's going to, yeah, that looks like an energy band diagram, but it's not. I put the charge in the floating gate. I store charge in there, and it increases the threshold voltage. So I get 2 levels of threshold voltage right there. And this is a single level SLC, single level cell. This is the high-end flash. I could do this, and we'll get to this later. I could do this. I could set 4 different values of threshold voltage there. And then I could read it here, and then decide whether I wanted to read it here or here, and store 2 bits in the same cell. And that's the MLC. They put that in things like the little flash drives that you buy that, you know, you carry around, thumb drives, SD cards. The single level cells, that's what goes into the enterprise level, the servers, the server farm stuff. Yeah, that is the multi, they can put 4 or 5 bits in one cell. Yeah. Another way of getting the memory density up.
Just a lot slower.
Yeah, I rearranged most of Brower's slides in here so that they go like this. DRAM has a destructive readout and flash has a non-destructive readout. So when I read the flash, those electrons, that charge that's in the floating gate stays there. I don't have to write it out again. If you have a destructive readout memory, you immediately have to write the value back in, just like you've had to do on the project. 2 different architectures. The one that made it took me a year or 2 before the NAND flash actually the daylight hit. Jack was in the classroom where I understood how it worked. NOR flash, I just pull the word line high, and when I pull the word line high, I'm going to turn this entire row of transistors on or not, depending upon what their threshold voltage is. And those 1s and 0s get fed right out to the bit line. It looks a lot like the way a DRAM works. Now, NAND flash is different, and I used to make up all kinds of things for how it works, and I thought I knew how it works, and this time I'll get it right. Can tell Jack I got it right this time. What I'm going to do is I'm going to select a string. Now, I select the string, and then I turn all of these transistors. I put a high enough voltage on all of these transistors, except for the one I want to read, to turn them on no matter whether they're programmed or not. And then I put this word line at V between the 2 threshold levels. Now this bit line will read the data out of the transistor that is not on, has a 50-50 chance of being on. All the other transistors in this string will be on. Their voltages are set high enough. And then I turn the ground select on. Now, the advantage to this is when I go through here, if I want to read out this whole string, I can read it out really quickly by just changing this one, turning this one on. I changed 2 of those, swapped 2 of those values, and I can read the next bit out really quickly. And the same time I've turned on all those word lines, I can read out all of these at the same time also. So it's a really long time to get all those word lines turned on within that NAND string. You have to turn all those word lines on. So it takes a long time to do the initial access. But once I get all these word lines turned on over here, and I'm just changing the voltage of 2 of them at a time, I can get large bursts of data. But that initial read, that initial turn on can take microseconds. I mean, it's years. Yeah, this one I can read out a little bit faster, and it's better at reading out small amounts of data. But we normally want to stream video and music and all this stuff at the same time right now. Download the 12 gigabyte file all at once. So we're looking at big blocks of data. So this is why NAND flash is winning.
Not have it take years to actually.
Right. Yeah. But it can sometimes take years to actually happen. Okay. These are just different ways they build it. It's kind of boring. What? Monday. Yeah, it's another big Korean conglomerate. Fujitsu, and again, it's just I don't want to talk about this stuff. I did that last time. The memory organization looks an awful lot like a DRAM, so it's not worth going through again. I have a memory array. I have row decode circuits that get their information from an address buffer that gets their information from an address that you send in. We've got column decode circuits. We've got the read and write circuits that data out. It looks an awful lot like a DRAM. The data in has to come in from the outside world. I got some kind of controller in here that holds all the registers that set up the memory the way I want it to, a little microcontroller for that, and can tell us the status and can also of those registers and can control how this memory is being read out and how fast refresh is happening, in theory. We couldn't make it slow enough, that was the problem. Okay, so we talked about this a little bit, and it's a little bit dated, but the ideas aren't yet. They will be next year. Inside your CPU, there's the register memory that controls how it's set up. That you want to store semi-permanently. There's this register memory, really, really fast. But again, it takes an entire flip-flop, pretty much, a latch, to hold 1 bit of data. So they're big and they're expensive and they're power hungry, and they're also volatile. If you turn the power off, you lose the memory. We have an SRAM puff. 1/4 of a nanosecond. And this is just relative. These numbers are all going down. We also, all this stuff is happening inside the processor itself. We also have level 1 and level 2 cache. This one's usually a little faster. This one's usually a little slower. These are even faster yet, but still it's a 1/2 nanosecond. But I can get a lot more memory in that cache than I can in the register memory. That's only like a kilobyte or a couple of kilobytes, depending on the processor. When I go out for my primary memory, this is for the programs that I'm using right now. I've opened up PowerPoint. So my PowerPoint program is going to be stored in primary memory, in my DRAM memory is what we're using now. It's really fast. This says 80 nanoseconds. I'd say right now it's maybe more like 20 nanoseconds. And you can get it in sizes like 16 gigabyte. Well, no, maybe let's say 256, 512 gigabytes for DRAM memory. My secondary memory, this is where I'm going to store my music. This is where I'm going to store the files I want to access. I'm going to store Microsoft Word there because I'm not using it at that particular time, and load stuff from my secondary memory into my primary memory. Like I've got a movie stored here. What I do is I want to watch the movie. I take as much of it as I can and I put it into DRAM, and where I can access it more quickly, and then just fill up the DRAM as we empty the old stuff off.
So you don't want SSDs to be constantly being used? Or?
You want them to be, well, this is the long-term storage for your computer. And it's an SSD now, it's not a magnetic disk anymore. You want, this is where you have the long-term storage, but if I want to anything I want to access in the next 5 minutes, I want that to continue to be saved in SSD, but also to be available in DRAM where I can access the individual pieces a lot faster.
If we didn't have DRAM, you're just running it all off the SSD. When you go to Word and you try to click the font drop down, it's going to take another 10 seconds to load all the fonts.
Yes.
They're not just all loaded.
Yeah.
in
Yeah.
DRAM.
Yeah. What he said. Yeah. If you kept your Microsoft Word, this is what Zach said. If you kept your Microsoft Word all in the SSD, and when you were accessing it, what would happen is I go to my menu and I want to change the font. It would take me 10 seconds to read all the fonts from the SSD back up there. But if I have all the fonts stored in DRAM, then I can access them much more quickly. Now, this is as it is now. I think this is a real possibility. I think all of this right here, and in the next 10 years or so, will be replaced by one memory unit, and it will probably be ReRAM or MRAM. I'm betting on ReRAM.
So we still need time. Universal memory.
The universal memory, the one memory to rule them all, and I believe it's ReRAM.
Hopefully we don't have to pull the RAM.
Oh, that's. It took me a little while to get that into part of it. I was thinking of the movie Joe versus the Volcano. I'm sorry, we had to. I flip movies. Okay. So this is what we have inside the flash cell right here. We've got 5 different regions of things that are going on. This is the bulk. This is the oxide between the bulk and the floating gate. This is the floating gate. I got another oxide here. And this is the, whatchamacallit, this is the gate contact. The gate contact we actually have a voltage tied to. Same thing we did before with the MOS structure. The Fermi levels have to line up. You can see that this is inside the floating gate. It's N type. This is P type. This is N type. And this is also N type. Oh, it's actually more of a conductive area. It's poly. And the energy bands have to go across there. I've got these big barriers between the floating gate and the outside world. So the only way I can get energy in there is I either tunnel across, where I'm an electron here, and I tunnel across this thin energy barrier and I end up over here, or I have to give it enough energy to overcome whatever that barrier height is. And that would be a more classical way of doing it. The quantum mechanical way of doing it would be tunneling. We can think about this as being a capacitor. You don't have a resistive coupling between these, but you do have capacitive coupling because this between the control gate and the floating gate, between the control gate and the floating gate, you have an oxide, so this is like a capacitor. And between the floating gate and the bulk, you have another oxide, so it's like you've got 2 capacitors in series. And you're storing the energy in between the 2 capacitors. Kind of like this. Gate, bulk, floating gate. So we want to just store charge at this node effectively. If we think about that from a circuit perspective instead of a band diagram perspective. So the control gate, there is some capacitance between that and the floating gate where I want to store the charge. That's what the big Q is for. And this is also capacitively coupled to the drain, the body, and the source of that transistor. So 2 ways we can get energy in. One is by putting a high voltage between the gate and the body, and the other one is by injecting, I'll talk about that later, injecting really hot electrons in between the drain and the source, high energy electrons. that one time when I was at ASU, they had the IEEE Hot Electron Conference in Phoenix in July.
Oh, no.
Dr. Ferry thought that was particularly funny.
Really hot election.
Really hot electrons. Okay. So when I'm running out of time, when we do the right operation here, there's basically what we're going to do. We've already talked about this. When I erase it, I set the threshold voltage of the device down into its lower level by getting all the electrons out of the floating gate. When I program it, I add electrons to the floating gate and I increase its threshold voltage. When I read it, I'm going to read it at a value, probably have a threshold value somewhere in the middle right here. If I turn on the transistor, I know it's erased. And if I don't turn on the transistor, I know it's programmed. And of course, the logic is backwards, so I always have trouble with flash. This is erase is a 1. When you erase it, you get a logic 1. When you program it, you get a logic 0, which really bothers me. Which just expect polarity issues here. Different types of flash memory, they all fall into either basically NOR or NAND flash. The flash guys at Micron aren't nearly as cool as the DRAM guys. I don't know what it is. There's just like a natural fit between all the NAU people are DRAM guys. That's probably it right there. Right, so 2 types of mechanisms for putting it in there. We've got to do some special processing. We need to grade these to support the higher voltages. And I'm sure you're really going to be a processing guy to get into that. You put for Fowler-Nordheim, we'll talk about Fowler-Nordheim later. A tunnel oxide for the tunnel, okay, whatever. This is kind of cool right here. I've got 2 transistors in series. I've got this transistor right here is the floating gate storage transistor, but I don't have a floating gate over here. So this is in series with a normal transistor. That's one way to put 2 transistors in series and take up very little space, is to make the actual control gate go across the whole thing and the floating gate only goes partially across there. Pretty easy processing step and you get a free transistor.
What the heck is the point of that? The second transistor is not storing your data.
Yeah, but you can use it as a select to turn it on. Okay. To choose which ones you turn on and off. Okay. We're going to talk about this a lot later, and I don't want to talk about this. ITRS was this wonderful thing we had up until 2016, the International Technology Roadmap for Semiconductors. There used to be literally hundreds of people doing processing, hundreds of different companies. So they would all get together and say, okay, when we go down to the next node, we're going to shoot for a 65 nanometer node. And then the people who are making, I don't know what this technology thing, the people who are making the equipment for that are shooting for a 65 nanometer node. Because there's only 1 or 2 equipment manufacturers. So they all kind of got together. They said, this is what we're going to do next. And this is, and it was wonderful. This is dissolved. And part of the reason why is getting to the next node, there's only 3 or 4 or 5 companies who are even trying and only 2 companies who are really getting there. So Samsung and TSMC, they rule the market. They tell the manufacturers what they want next. there isn't a lot of, there's not competition, there isn't a lot of competition at 3 nanometers. And even Intel's starting to fall out of the race, because they're stuck at 7 again. Yeah, that's fine. AMD made this brilliant decision to just have TSMC build their processors. And that's why they're screaming ahead while Intel's still trying to figure out how to get down to 7 nanometers. Yeah. This is memory sizes, and you can see they're going down with time. And I did a quick calculation to figure out what it was in 2021 based upon the last information I got. You just add another 0 in there. They keep shrinking, and that's in micrometers squared. It's about 81. It's really about 81 nanometers squared. So we keep getting higher and higher memory and smaller packages. We stack these memories on top of each other, and we get it even faster, even more so. And you can see with time, everything, the size of all the cells have been shrinking fairly consistently. And we get more memory in a smaller space, and memory gets cheaper bit, and so we use more of it. So we just store 20 times more cat videos because we can.
Yeah, videos, music.
Yes.
All fun stuff.
All the important things. What? And you can lose your homework. My hard drive ate my homework. This is the 1T, 1C cell, and all the dimensions are shrinking. Every time I talk to Micron, they're down at another size process. The final exam, Thursday, April 29th, 12:30 to 2:30.
Oh boy, the final exam's really soon.
Well, no, I know that's what I was shooting for to get here, but obviously I didn't. Wait, that's March 29th.
Yeah,
We're before that.
We were before that. Okay, good. Oh, good. I know, because we got pseudo spring break. I don't know what's going on anymore. We got caught up, and we are done.
Yeah.
Any questions or other ramblings, or maybe I should do the roll again because I was like listening.
The modern day equivalent of my dog ate my homework is my dog peed on my computer, and so I don't have my homework anymore. Someone in my CS345 class said that the other day.
Okay. I actually had this happen. We had the last school I was at, we gave them textbooks. It was part of their tuition. So they all got the same textbook. And the kid comes in and goes, I can't do my homework. My dog ate my textbook. And he actually brought in the textbook. It was all chewed up. It does happen. Any real questions? Hamad, Benjamin, you're not here. You dropped. Not Benjamin, somebody else. Nolan is not here. Isaiah is not here. Work on your project. You dropped. And Shujan will watch later. What? 2 people. Yeah. One of them was having 2 of them were having technology issues. They just couldn't. Yeah. Okay, stop recording.